Thank you, Teresa. So welcome everyone to our Tech Talk today. We're going to hear from some really smart researchers from our Florida University system. They're going to talk to us a little bit about smart manufacturing and then what they're working on, but also what is coming next in their research labs. This is all applied research for pushing forward manufacturing productivity. All right, so we have, let's see, hold the introductions till, I guess we have the picture slide coming up, so let's go to the next. So I'm Marilyn Barger. I'm the Senior Educational Advisor for the Florida Advanced Technological Education Center, and we're part of the Florida Makes Network. Previously, we were funded by the National Science Foundation and have now been integrated into Florida Makes, which is the Florida MEP Center, and that's the Manufacturing Extension Partnership. So talk a little bit about FLATE first, and then go into our presentation, and then get into the panel questions and questions from our audience. So, well, this isn't the updated slide, but this is who we are. We're funded in part by the Florida Department of Education and their Perkins 5 State Leadership Act. And we're also funded and supported and hosted by the Florida Makes Network. We just talked about who they were, the MEP Center for Florida. And also we're funded by some special projects from the National Science Foundation Advanced Technological Education Program that funds technical education at 2-year degree and awarding institutions. So sometimes a 4-year institution has a 2-year program. So any of those would be eligible for funding from the National Science Foundation ATE program. So like everyone else, we have a vision, and our vision is to drive Florida's world-class manufacturing workforce education and training and all the systems. And there's no better way for us to do that really than to partner with Florida Makes and get the educators and the students as close to as many industry folks, and in our case, manufacturing, as we can. So being part of the Florida Makes Network really facilitates that, and we're looking forward to really optimizing that opportunity in the years to come. So next. So we do this work with the schools, starting at the 2-year manufacturing education programs and working down to the pipeline and working up through articulations to 4-year programs, working with curriculum reform and development. In that regard, we work closely with the Department of Education, Career and Technical Education Division. We do outreach and student recruitment. We all know there's a workforce crisis, and certainly recruiting students into these programs is an important part of our work right now to try to get more of them out so they can start to work for our industry partners. To make the best programs possible, we do professional development for educators. That might be through technical information and training for new technologies, or it might be for new educational technologies, new pedagogies, new ways to teach to better inform students and better prepare them, provide better access for more students as well. And lastly, we dabble in technical education research, technician education research, trying to find out who our students are through a research lens, and that can help us better serve them as students and address their particular needs. All right now, before we go into the tech talks, I want to introduce Ernie Friend. Ernie Friend has taken my old role, which was the executive director of FLATE, and I'm excited to be turning over that position to Ernie. Ernie, you want to say a couple words?
Welcome. Yeah, hello everybody. Yeah, big shoes to fill, but certainly I'm really excited to be part of the FLATE team, working with Teresa, Daniele, and of course Marilyn. This is a great series. Certainly, I will continue, with Marilyn's support, continue the series. So if you're listening today, if you're in the audience today, or even if you listen to the recording later, you have some ideas or maybe some people that are doing some interesting research, please reach out to us and let us know what you think and maybe some ideas for the next set of series.
Yeah, thanks, Ernie. Ernie will be hosting in the future, so it won't be me behind the curtain. It'll be Ernie, and we'll be looking forward to adding to our portfolio and getting more people involved in these talks and sharing with everyone who's on the line right now. So without further ado, the order of the day will be, we're going to have these short presentations from our three guests. Dr. Gloria Wiens from UF. All three are mechanical engineers of some sort, or from departments with mechanical engineering, some with aerospace. So she's at the University of Florida. We have Dr. Nancy Diaz-Elsayed, and she's from USF right here in Tampa, where I'm located. Also a mechanical, and then Dazhong Wu, assistant professor from UCF. So they all work in mechanical engineering related to manufacturing systems. So we're going to start in the order you see them from left to right, and we're going to turn the screen over to Gloria. Ready to share your slides?
Yeah. All right, everybody can see them?
Yes.
All right. Thank you, Marilyn. Again, it's a pleasure to be here again. And also back in November when I did the long webinar. My topic is cobots and automation, and this is also my area of research here. And with the onset of Industry 4.0 and 5.0, basically being coexistence, there is a greater demand now for human and robot collaboration that's in manufacturing here. And what I have here is Industry 4.0 is known to be more technology driven, where Industry 5.0 is more value driven here. And I've identified two of these six enabling technologies associated with Industry 5.0, which is the individualized human-machine interaction technologies that interconnect and combine the strengths of humans and robots and machines. And then there's also artificial intelligence to detect, for example, causalities in complex dynamic systems leading to actionable intelligence. And one thing I've added on there on the edge, I put it on the edge for a purpose because there's also the advances in edge computing is starting to be more and more prevalent because in actually enabling cobots and other types of automation, in that we're now having so much data collection and how to manage that and be able to react in real time. So it's given the flexibility and ease of implementation for real-time performance. Collaborative robots are a form of robotic automation built to work safely alongside humans in a shared collaborative workspace. And with combining the strengths of humans and robots, the goal in manufacturing is really to have that fenceless robotics automation, where robots just simply work side by side to physically assist the human workers. And there's different levels of that interaction currently used in industry, which is shown here by the four levels in the pictures there, which the level one is the very basic. There is you basically, once a human crosses a threshold, is basically enters the workspace. It's kind of like the fence, but yet fenceless. Basically, the robot stops what it's doing and waits till the person clears the workspace before resuming action. In this SMS, basically, you're having all the actuators remaining active so that the robot can respond more quickly versus shutting down. The level 3, right below it, is basically enhancing that by having different zones. So basically, the robot simply just slows down depending on how close the human is and how fast they're moving close into the workspace, and just slows down and eventually stops if needed. And that way you keep it with higher level of productivity in doing so there. The other one that's very important, of course, is the power force limiting, which is basically using sensing within the joints, their torque levels and so forth, that you can then detect, okay, if there's a change, there must be a collision, therefore the robot can respond and keep the force levels of contact at a lower level, so as to minimize any injury here. This slide really shows some examples that I had in my webinar back in November, where if you look on the left, you see the woman there. She's in direct contact with the robot. In that one, you're really synchronizing the different tasks of assembly, where she does parts of it and the robot does parts. But sometimes you get the timing out of sync, and therefore you might have a collision. And then with like the force power level type cobot, you can actually prevent actually the levels of forces of contact being less, so it doesn't hurt the person, and the robot can respond and back away. Welding is another common area for teaching welding, using a cobot and then having it play back. You have cobots assisting with basically carrying the heavy load on that, which is in your upper right corner, and then palletizing is also a very common application there. And those are some industries there in the pictures, and then I listed some of the other leading manufacturers in cobot, basically collaborative robots, which we call cobots on there. Challenges in the state of the art. For those, you basically have, you're finding basically that the priorities such as safety and productivity may be conflicting objectives on there, because if you have the robot stop every time the human enters the space or within proximity, then you're eventually going to start having significant delays in your manufacturing. So how do you get it more coordinated and seamless and less interruptions there? And so one is, of course, knowing the physics and the fundamental limitations, but you have to take those tasks that's being done within the work cell and break down the complexity so that you can now divide the task more efficiently between the human and the robots and machines on there. And then how do you make adaptation to that when changes happen in that process? The other thing of concern is, and which has a lot of research, is the trust. And that can go both ways. There's the robot trusting the human by seeing its behavior and knowing how to respond. So it's basically its trust level, or whether humans move a certain way. And then you also have, of course, the human trusting the robot. What is that comfort level for the human to work with the robot on there? So every person has a different comfort level. And so you have different operators that come in as you change shifts that will impact the efficiency of the cell. So risk management, risk reduction, looking at the intent, both human and robot. You have sensory feedback. And eventually you have the two-way communication right now is really push a button on the robot if you want, once it's stopped, to get it going, is what industry's using a lot in there. Integration of cognition, perception, and prediction is where we're headed for augmenting the intelligence of robotic systems and to enable greater human-robot interaction there. So I call it the bridging of sensing and artificial intelligence with mechanical and physical necessities to successfully augment the robot's awareness and intelligence on there. So this is some samples of advanced sensor technologies that are being incorporated into cobot situations on there. Of course, some are we pretty much used to, like there's a lot of RF signals throughout. So my colleagues in Italy at the Institute of Intelligent Industrial Technologies and Systems for Advanced Manufacturing, who I collaborate with, they've used these RF signals to detect presence of where the human might be, because from all the different signals, they can get a pattern there and determine what the human in general, what they're doing. You have time of flight cameras. There's also infrared, LiDAR, the wearables. So you have the inertia measurement units to measure motion of the human. You have EMGs. And now people are looking at EEGs, basically looking at the brain waves to determine the interaction that one should take with the robot and the human in the environment there. On the right, you see some skeleton tracking, like it's really just tracking the human with markers. And they basically gathered information where the probability of the human is going to be within a certain volume of the work cell, so that the robot will know not to plan any motions through those volumes if there's a high probability the human will be there during the process. For my research, I'm looking at the integration, the seamless integration of both of sensing, cognition, and prediction. I'm teamed up with 3 other universities, Stony Brook University, Case Western Reserve University, and Missouri University of Science and Technology. We also partnered with with STEMA, which is the Italians that I just mentioned in the previous slide there. And so for my team, we're the action team because we're the integration. We make all that cognition, sensing, and prediction come together and action occur by the robot working with the human. So we're coming up with an efficient, proactive, adaptive collaboration intelligence within building that within the control system that the robot itself, augmenting its intelligence. So you still have the underlying control that you're used to, but you're augmenting it with intelligence here so it can have better awareness. So basically it's to ensure the safe interactions with humans and to mitigate any production disruptions there. So the key to us is the segmentation of those tasks, breaking it down. You know a lot of it ahead of time. So you see that what I call PASI is both online, real time. I actually my students actually built into some offline because you know a lot of what's supposed to happen. So you can use that as a baseline and segment that. And then as the human does something different or something occurs, you then have the ability to redefine what the robot's doing. If you have it predicted far enough in advance, you can do it proactively so it's very seamless in the integration. And then the robot, basically cell hopefully will be more productive. That's our goal there, as well as safe there. So for example, if a human comes in and instead of the robot just stopping, it may say, well, I'm going to go over and work on another task while I'm waiting for the human to get done in this space and then come back to that. And so it's still, keeping that productivity going. There is challenges. So you see here the parent-child human kinematics. The cameras in the system don't always detect, they can't, you have occlusions there. You can't see where the whole human is, what at least the key parts. You don't necessarily need to know the legs if you're working at waist above. But so things are missing. And so how do you make sure that the robot doesn't actually go there thinking there's no arm there when there really is and actually have a collision there. So we have basically doing some patching in the kinematics there based on the collection of data collected there from the cameras in this case. We also look at skeleton. You see also on the right is this here is basically predicting the human motion and where a collision might occur. This happens look like a base there, but that really is a robot in its vertical home position. And the student was just using that as its reference to show collision there, which is these red marks here on there, which and it basically is time and space. So if there and the robot's there, then there's not a collision. So we have a combination of time and space so we can detect when a collision might occur if the person happens to be there at that instant in time. So those are key together there. And quaternions is again just a kinematic relationship to define the position orientation of each of the links of the robot on there, as well as the human skeleton on that. Again, there is challenges there. Sensors are not always that good. You have occlusions, resolution may not good, but you got to look at in terms of if you're introducing cobots into your environment, some takeaways is, of course, you want safe. You want space, it's generally giving you some space saving because you can reduce the work cell size. It gives you flexibility and low cost there. Now, I got a quote here from Paul Santi from FANIC, where my student actually just finished an internship there to get to see what their challenges are with the robots. So he has better insight to what industry is doing as he works on his research. So basically his quote was, design your application for collaborative, but don't force it. So if it's not the right application for it, you don't want to force it. You want to use collaborative where it enables you. And there's also multiple forms of collaboration, different levels on that. So look at your goals on making sure you're achieving it. Don't, just don't jump on the bandwagon. Just make sure it's the right thing for you at the right time. However, my other takeaway I want you to take is be open and innovative in your mindset, because technology is advancing all the time. Like edge computing is now coming more and more prevalent there, allowing us to manage data more effectively and use it in real time on that. So basically look at the ways you can augment the intelligence of your systems on that. And again, thank you. And I hope I didn't go over too much time, but again, this is fun. My project research is funded by National Science Foundation. And this is my team here, which we call the action team.
Okay, Great, thank you, Gloria. That was awesome. I remember seeing the in the full presentation that you did in the fall. The students had a nice video of that. So if anyone wants a little bit more visualization of those activities and working on that, they could go back and watch that first, the Tech Talk. I think it was November, right?
Yeah, November.
I think we'll move right now to Nancy. I see her slides are up, so I'll let you take it away.
Thank you, Marilyn, and good morning, everyone. It's a pleasure to be here today. And so I am following up on our January Tech Talk on tool condition monitoring for CNC machining. So as Marilyn mentioned, I am the director of the Smart and Sustainable Systems Laboratory within the Department of Mechanical Engineering at the University of South Florida. And I just wanted to start off with this evolution towards smarter manufacturing, since today's panel is focused on Industry 4.0. So we're aware that, we started off with small, customized products, essentially craft production in the 1850s, moving towards mass production, flexible production with the onset of computers and robotics, and have traversed towards mass customization. So we have a multitude of different types of configurations for products nowadays that can range drastically to lower, much more achievable features like different types of paints versus completely different subsystems introduced into our complexly engineered systems. And so to give an example of smart manufacturing, taking a deeper look at maintenance, in visiting and speaking with a multitude of different types of manufacturers, we find that there's often employed a reactive approach to maintenance with some elements of preventive maintenance. So reactive being when something breaks down, when a piece of equipment breaks down, then we go ahead and we bring on a maintenance engineer to fix that component. And preventive maintenance constituting, a predefined schedule for maintaining specific components of that piece of equipment. So this is fairly common within the manufacturing sector we've seen, but we're moving more and more towards smarter manufacturing systems. So enabling the improved maintenance and manufacturing system by using predictive analytics. And even nowadays, there are some pieces of manufacturing equipment that have some self-monitoring capabilities where depending on the existing process conditions in real time, those process parameters can be optimized in order to enhance the performance of the piece of equipment. And so much of our research is focused on how we can enable manufacturers to implement and leverage smart manufacturing technologies in order to have more sustainable operations over their lifetime. So we largely focus on SMEs, or small to medium-sized enterprises, because they make up the vast majority of establishments across the US. But we also realize that there are quite distinct differences between SMEs and these larger multinational enterprises. And with that, there are different hurdles that need to be overcome in order to enable the adoption of Industry 4.0 technologies. For example, multinational enterprise might have that very large breadth of expertise, very high access to financial resources in order to have the high adoption of advanced manufacturing technologies, whereas SMEs might have lower efforts related to research and development, but very high nature of product specialization and very focused knowledge and experience. And so in thinking about a more specific example, the process of trying to manufacture and assemble health ventilators, for example, early on in the pandemic, it required the contribution of a multitude of different manufacturers, and only specific SMEs or contract manufacturers had the capabilities of manufacturing important subsystems, critical subsystems, such as the pistons of these health ventilators. So we certainly want to enable manufacturers with the work of our research laboratory by introducing smart manufacturing technologies that have lower barriers to adoption. And so one of the research areas that we work on is around tool condition monitoring for CNC machining. Focus on CNC machining because it makes up quite a large portion of the manufacturing processes within the sector. Overall, the CNC machine tools has a market size of about $82 billion. It includes, milling centers, drills, turning centers, grinding machines, and more specifically, we want to be able to stop tool failure as it results in the unscheduled stoppage of the production line, and it results in negative impacts, time lost, increased capital expenditures. And so this is all, of course, negative to the manufacturer at hand. And tool condition monitoring systems help to inform the operator as to when the condition of the tool has degraded enough such that the cutting tool needs to be inspected and possibly changed in order to maintain the tolerances needed for the parts being manufactured. And so talking more specifically about tool wear, there are a number of different factors that cause cutting tool wear in real time: mechanical wear, cutting heat, as well as chemical wear. So through these wear mechanisms, the composition of the cutting tool can become degraded over time. And on the left-hand side, we see some close-up images of what's known as flink wear on an end mill, more specifically. And so in our laboratory, we conduct experiments. We're focusing preliminarily on vibration and power analysis in order to detect the condition of the cutting tool. We have a LMV 400 that we're using, a desktop milling center, and we are machining different types of materials. The experiments presented herein are focusing on aluminum 6061 and cutting with a 2-flue carbide end mill. And so with our vibration analytics, we're conducting a fast Fourier transform in order to find those key frequencies at which the machine tool is vibrating during the machining process. And the power analysis, we're using a watt node Modbus in order to look at the aggregate power demand of the machining center, but we're more recently also submetering the spindle motor in order to see more closely what the power demand of the spindle is over time as well. And so here is a short video that was also presented during the prior tech talk. But as you can see on the left-hand side, we have the power demand over time. And so when we see this initial peak is when the spindle motor begins to run. And then this is just traversing through the work volume. And we see another peak when we actually start removing some of that aluminum 6061 material. And so you see that there's a very specific profile for this machining center, even as the servo motors along the x-axis are kicked on. This is the second spike that you see here. And then once again, we start the removal of material over a slot for that aluminum workpiece. In the bottom part of this video, we have the acceleration. So we're measuring the acceleration across 3 different axes, the X, Y, and Z axes. And so you can see here, 1G is where we're measuring our Z axis acceleration. And so what's more useful for the accelerometer data is that raw data. So we can process the data, conduct a fast Fourier transform, and see how the changes in the key amplitudes occur over time. So diving a bit closer into the power demand. So this is a snapshot for the slots that were cut on the aluminum workpiece. And we can see, interestingly enough, that as the cutting load varies, so does the power demand, which is what we expect because the power is correlated to the cutting forces of the machining process. And so this initial slot actually has a lower material removal rate because we're not at the full diameter of the cutting tool, whereas slots 2, 3, and 4 are the full diameter of the cutting tool, and slot 5 is slightly lower. So that power demand for the machine tool is quite representative of what's actually going on in terms of the operations of the machine tool. When we compare a worn versus a new tool, we expect higher cutting forces for the worn tool, and we can visualize them here about 0.57 watts higher when we're removing material with a worn tool relative to a new tool. So we're able to identify the condition of the cutting tool, in this case with the power demand. And similarly with the vibration analytics, we conducted the fast Fourier transform, and we're comparing a new versus worn tool, and the vibration, the amplitude of vibrations are higher for the worn tool versus the new tool, which once again we expect because there are higher cutting forces that are experienced during the machining process. And so I'd like to acknowledge our funders for this research, the Alfred P. Sloan Foundation, the Social Science Research Council, the College of Engineering at USF, as well as the USF Nanotechnology Research and Education Center for the use of their metrology, in addition to the members of the S3 laboratory, which contributed to this research effort. So thank you very much. And I'll pass it back over to Marilyn.
Thanks, Nancy. So I always think about preventative maintenance. You know, they tell us we should do that at home. We should do whatever, you know, even clean your roof instead of leaving leaves on it, which is the status that we're in right now. But we don't think about how it affects industry really on a day-to-day basis, and the cost that's associated with it for the tools wearing. When we teach machining, we teach the students to put the new tools in and start the machine and make the piece and mention the idea of preventative maintenance, but not ever do much with that next piece of, well, how can we change that? How can we minimize that? So, and what are the factors that we might want to change if we're actually in business and trying to make parts for a living, that the tool just won't last forever, just like the knives in my kitchen drawer won't always be sharp. So anyway, let's move on to our third. I don't see any questions, so let's move on to our third panelist. Are you ready to roll? I see your slides up, Dazhong, so I'll let you take it away.
Sure. Okay, it's my pleasure again to be part of the panelists. My name is Dazhong Wu. I'm a current assistant professor in the Mechanical and Aerospace Engineering Department at the University of Central Florida. Today, my talk is about applications of artificial intelligence or machine learning or data science in manufacturing. And here is the very brief overview or summary of my current research projects. So my research project currently being funded by National Science Foundation and also MXD, previously known as Digital Manufacturing and Design Innovation Institute, which is one of the third Manufacturing USA institutes. So my research focused on actually developing predictive models for manufacturing processes and also complex systems. So as you can see from these slides, we developed predictive models or data-driven models to predict cutting tool wear in machining processes, and also predictive models to estimate material removal rate in chemical mechanical polishing processes, which is one of the most important semiconductor manufacturing techniques. And also we monitor melt pool temperature during metal 3D printing processes, in this case, directed energy deposition. Actually, we also use machine learning techniques to predict melt pool temperature, which actually affect quality of the 3D printed parts significantly. We also predict so-called remaining useful life of very common mechanical components and systems, such as bearings, gearboxes, and also we predict so-called capacity fade or discharge capacity of lithium batteries. So this is a very brief overview of my current research. And in this, today I'm going to only focus on data-driven smart manufacturing. So I will only talk about 2 projects we completed so far at UCF. So the first project is about prediction of melt pool temperature in a metal 3D printing process. So as you can see from this figure on the left and right, so this is our experimental setup. So we actually equipped metal 3D printing process with an AR camera, and we use this AR camera to capture thermal images in real time during this metal 3D printing process. And you can see on the right-hand side, you can see one of the captured thermal images, where we can measure actually the temperature of within this melt pool boundary. And as I mentioned before, this melt pool formation process significantly affect quality and also the defects within the 3D printed metal parts. And this slide shows our numerical results. Actually, we built 2 machine learning models using 2 very effective and very powerful machine learning and deep learning algorithms. One is called XGBoost. The other one is called LSTM, long short-term memory. So XGBoost is one of the machine learning algorithms. LSTM is one of the deep learning algorithms. So as you can see, using both algorithms, we built two different prediction models. And as you can see from the figure A at the top, we plotted the actually the predicted temperature and also the actual temperature versus actual time. And you can see this the actual temperature, output temperature, is in a very good agreement with the predict temperature by XGBoost and LSTM. And also we further quantify prediction accuracy of these two algorithms using RMSE, root mean square error, and also mean absolute percentage error. And also we quantify the training time and try to see which algorithm is more efficient. So as you can see, both algorithms achieved pretty high prediction accuracy in terms of root mean square error, RMSE, and also pretty high or pretty low relative error, mean absolute error. One is only 1%, the other one is 0.8%. But if we compare the prediction efficiency or training time, actually the conventional machine learning algorithm XGBoost actually is very efficient, more efficient than LSTM, which is a deep learning algorithm, which takes more than 100 seconds actually to train a model. But both algorithms, as I said, actually achieve pretty good prediction accuracy. And we also compared our results with the state-of-art techniques reported in the literature. So we compared our methods with analytical model, with finite element model, and also convolutional neural network, which is another deep learning algorithm. So as you can see, comparing with the first 3 studies, so actually our methods achieved lower RMSE and also lower MAPE. In other words, we achieved better prediction accuracy. And if you are interested in more technical details, actually you can download this paper, and maybe you can find more details about the models and how we build a model, what are the input monitoring data, and what is our output, and how we make predictions. The second project is about predicting material removal rate for chemical mechanical polishing, also known as CMP. And the CMP actually is a process that smooths the surface of silicon wafers with a combination of chemical and mechanical forces. Because this process involves not only mechanical forces, but also chemical forces. That's why this is quite a complex process, and it's quite complex and difficult to predict material removal rate. So in order to, if we can accurately predict material removal rate, actually we can achieve very high level of uniformity of the silicon wafer. That's why we want to predict material removal rate. And oftentimes, so CMP is applied between deposition and the patterning processes to remove excess materials and also eventually to maintain flatness. So this figure shows basically the schematic diagram of the CMP machine or tool, which involves several key components such as CMP polishing pad and also polishing pad conditioner and wafer carrier wafer, polishing slurry, as well as rotating platen. And basically, so we polish the polishing pad shown in this schematic diagram, polish the surface of the wafer. And at the same time, we use this pad conditioner refreshes the pad surface in order to maintain constant asperities. So this is a key idea behind this technique. And again, we build, in this case, a so-called physics-informed machine learning model to predict material removal rate for CMP process. So in this case, you can see we plotted the material removal rate MRR in nanometer per minute versus actually the sample index. So we actually collected a large amount of data using over 2,000 wafers to generate our training and test data. And also we evaluated the prediction accuracy in terms of, again, root mean square error, RMSE, and also relative error. So in this case, you can see from figure B and figure C, so we quantify the error. So RMSE is about 15.7, and the relative error is about actually 11%, which is a pretty good prediction accuracy. And then again, we want to also compare our results with state-of-the-art techniques. In this case, we compare our results with a well-known model called Preston equation or Preston model for chemical mechanical polishing processes. So as reported in reference 1, so this group of researchers achieved RMSE of 29.5 using the same data sets. And in our study, we actually, using this physics-informed machine learning model, we achieved almost half of the RMSE root mean square error, which is about 16. So if you're interested in the more details how we built this physics-informed machine learning model, actually you can refer or download this paper. So I want to emphasize the unique attribute of advantage of this approach. So we actually combined a underlying physics or analytical solution behind the CMP process with a machine learning algorithms. In this case, we can leverage both underlying physics and also data science in order to achieve the best prediction accuracy, rather than using purely data-driven or physics-based methods. I think that's pretty much all I have. At the end, I want to acknowledge my students and also my sponsors. Thank you.
Okay, you want to go ahead and stop sharing? So we have some questions for the panels, but first I think before we do that, maybe we'll ask if there's any questions from the audience, anyone who's out there. So lots of detailed research work that impact how work takes place in a facility that's making something, all the behind the scenes or before the scenes research before we can actually use things and fix problems or fix issues to make manufacturing more productive. So I think Dr. Gilbert said he had a question. You want to unmute?
I can indeed unmute, and I can even show the video. My question, actually, I have a question of each of the participants, and each of the presentations was really very, very good. So I will start with the first participant. Gloria mentioned edge computing, and my interest primarily is the floor engineer and the support technician on the floor with the manufacturing process. So how do you see new skills in the BS level engineer? In this case, I guess it might be a mechanical engineer, but usually the floor engineer can be chemical, mechanical, electrical, etc. How do you see the edge computing skills getting involved with the education of those folks, that is the new engineers and the technicians?
Thank you. It's basically, as technology advances, we keep incorporating it further and further into classes, but that is always the challenge of getting the right like software do they learn and so forth. That's always the challenge because technology changes. And sometimes we're behind the curve on that, but I think it's more educating them so that they can adapt to any different system, because understanding the fundamentals are the same within, like programming and so forth, the logic, and then getting through their assignments actually using those. We do have a lot of laboratory courses where they learn, how to take data and how to process it. That's key for that. They, in their design projects, they learn that. Now it depends also their interest, how deep they go in learning that. Each student has a different interest, and mechanical engineering is pretty broad into the specializations, but it's more and more is getting in there. And at University of Florida, we have our claim that we will be the first university to have artificial intelligence integrated into all curriculums, not just engineering, so that the students have more appreciation, awareness, and that's where Edge is in between all that. Edge is actually allowing us to manage the data, to bring that AI, which is a lot of data, and bringing it into the actual physical, domain there for like the controls that we're showing today on that. So it's kind of hard to say exactly which one, but again, we keep advancing that integration as it comes on.
Okay, thanks. Shifting a little bit south to USF. Nancy, you were focusing a bit on maintenance during your presentation, and there is certainly a Industry 4.0 concept called overall equipment efficiency. How do you see that concept fitting into the same thing, into the education of new engineers and new technicians?
Oh, that's a great question, Dr. Gilbert. And so in our work, so I'm also working with the standards development team related to prognostics and health management for manufacturing systems, and overall equipment efficiency is, what we always go back to. And so Industry 4.0 enables us to do real-time monitoring and to understand how that equipment is performing over time. And with TCM, we are certainly helping to improve the availability of the pieces of equipment such that they're not we don't realize that downtime over significant periods of time. And so I think that there's an opportunity across different levels of education. OEE, we speak more towards mechanical engineering, so our bachelor's students taking manufacturing processes, for example, but then also higher level degrees like master's and PhD students who are more focused on processing the big data and having the bigger perspective on data analytics for the production process as a whole. And so that spans and not only mechanical engineering, but it also starts going into computer science and industrial engineering as well. And there are certainly opportunities for two-year degrees to implement such solutions and improve the OEE of production systems. And the type of education that could be facilitated, though, it differs across these levels. But for example, at the AS degree level, something that could be considered is related to the statistical analysis. So at what point do we understand that there's a statistically significant change between the production system itself? So not having to dive too deeply into big data or data analytics, but just enough to realize when process changes need to occur within the production system.
Thank you. Thank you. Now moving a little bit east on the I-4 corridor. And Zhenyong, you mentioned, or your talk was focused, and a nice talk as well, on machine language and artificial intelligence. There is a distinction there. And my focus would be, what does the new engineer and what the new technician would have to know as floor engineers about either relative to operating and maintenance situations?
Do you mind repeating or rephrasing your questions? My understanding is how machinists, how much they should know about machine learning or AI as a mechanical engineer. Am I right?
Yes, that's good. Thanks.
Okay. I think this is a very good question because oftentimes a lot of students, before they register for my class, oftentimes they ask me how much they need to know machine learning or AI, and how much they need to know programming. I think so. Oftentimes, mechanical engineering students, I highly encourage them to take at least one computer science course at undergraduate level. And I think in this way, this will help them to at least have an entry level of programming skills. I think with just a bachelor degree mechanical engineering students do not need to really have a very deep understanding of machine learning algorithms, because our goal is not to develop very new machine learning techniques. Instead, I think our mechanical engineering students should be able to determine which algorithms should be best suited to solve a particular manufacturing problem. And oftentimes, so these are well-known existing algorithms, students do not have to start from scratch to implement a particular algorithms. They can find a lot of open source programs online. They can also find a lot of toolbox, let's say in MATLAB, which is not quite difficult to implement. So I think this is the current situation, and I think how mechanical engineering students should get familiar with AI at this type of level. Did I answer your question?
Yes, very well. Thank you very much.
Thank you.
Did you want to comment on what about the two-year technicians and their knowledge of AI? I think he also asked about that. If you
For the two-year technicians, actually, I have been working with two machinists at UCF machine shop in our department. I don't think it's too challenging for them to pick up some relatively basic programming skills. For example, I work with them on teaching them how to use MATLAB, and they can easily know how to call certain toolbox, certain functions in machine learning toolbox, and they can easily pre-process some raw data, let's say some raw signals from, let's say, accelerometers, dynamometers, or thermocouples, and they can run some simple machine learning algorithms on this data to at least plot the predicted results. I think it took us maybe a semester also for these two technicians to be able to collect raw data using sensors and also analyze this data with some very basic, relatively straightforward machine learning algorithms in MATLAB. Of course, without MATLAB, using more other open source, let's say Python, is a little bit more challenging. But I think if two-year colleges purchase MATLAB, I think it's relatively straightforward.
interesting. That's some good advice, because I don't think too many of them do use MATLAB or teach it specifically in the two-year programs. But we are starting to deal with more data that they have to interpret, machine data of different kinds coming from different systems to evaluate as they're working on their, particularly when they get to the stage of working on some projects. So certainly that's an important piece, and maybe that's a good thing for us to start looking into. So I don't see any other questions here. We did have some specific questions we were going to ask the panel. I'm going to skip the first one. We've talked about Industry 4.0, or maybe we'll move to what they think Industry 5.0 is instead. We had somebody mention that. I think it was Gloria earlier. And what's the big buzz with Industry 5.0? What is that going to add to, and maybe what is it going to take away from systems that would be considered now Industry 4.0? Anybody want to jump on that?
Well, for Industry 5.0, it's bringing in more the human element into the automation. That was the key thing, that in terms of the 6 enabling technologies, that human interaction with the equipment and the robots, in this case, on that. So that's where I see Industry 5.0. So basically, it's bringing in that more the human element there as we look at advancing automation there.
So working directly with the machines in the interface.
Yeah, so it's towards the sustainable, human-centric, and resilient, according to the European industry definitions.
I gotcha. So sustainability is a kind of separate focus for that.
Well, there's like sustainable, but also the human-centric aspects to it to make it more sustainable on that.
I
So,
see. Okay, okay.
Yeah.
Anyone else want to comment on Industry 5.0 or where you see it, your work interfacing with that? Nancy or Dazhong?
Yes, it was very exciting to see the incorporation of the environmental aspect of manufacturing systems, because we think about Industry 4.0 as the cyber physical systems. We're able to predict, you know, the remaining useful life of components. We're able to improve the productivity of our manufacturing equipment, now bringing in that human element while taking into account the impact of the environment. And so part of our work with the Smart and Sustainable Systems Laboratory is leveraging a smart manufacturing technology so that we can improve the sustainability of manufacturing operations. So we're excited for what it has in store.
you want us to go further on that? Again,
The piece from industry for sustainability from an environmental engineering perspective was always all of the nasty stuff that was the waste products and the pollution that was out there, and we had to control everything kind of outside of the industrial envelope. The extra trash and minimizing that, mitigating that was kind of the focus of our role as when working with industry. And so it's interesting to think about it from a different lens and looking at it inside a facility. Interesting.
Certainly, and inherently, sustainability has three core dimensions. It has the environment, the economic dimension, as well as the social dimension, where we bring in the human element as well. So it's all encompassing.
That's great. Gloria, did you have another comment? It kept popping up in my window.
further is
No, okay.
pulled all together.
Oh, I think we already talked a little bit about the role of the question number 2, or Dr. Gilbert really grilled a couple of you on what the technicians would need to know, which is ever present on our mind as to what we should be teaching in the classroom for the 2-year program. So let's see what's on the next screen, or these last 2 questions, if we have time for them. So the question number 3 is, where do you think your research is heading? And I'll just put out the next one also, if you want to comment on either as kind of closing statement, that there's a lot of talk about convergence and converging technologies, and where do you see that in your own work, or what do you think that is going to look like in the future?
I guess I'll go ahead. I see really my work is going to realizing the Industry 4.0 and 5.0 integration there and merging together, as well as for convergence. I'm seeing like the edge computing is going to be, I think, critical for me to get the real-time implementation of all this augmented intelligence and prediction, so as to make everything more seamless and safe.
Okay, great, thanks. Anyone else? We got one more minute. Any comment on these? Okay, well, if not, I guess we'll say thanks for participating today. Thanks for joining us, everyone who is here. We do have one announcement. There will be one more webinar related to Industry 4.0. This is going to be hosted by the Florida Makes Network. The technology committee is starting to roll out some sessions. And so this was in a couple of weeks. It's going to talk about manufacturing automation leaders what do they have to say about the current and future state, and you'll see who's going to participate in that particular panel. R&D Automation, Adams Corporation, Adams Automation, and also Roots Engineering, who both of whom or all of whom work with the colleges at different levels. I know they work with the two-year institutions in Florida, providing equipment and stuff like that. And I'm presuming that they also work with the university. So some of you probably know those, some of those folks that are listed there. So we'll put the registration link in the chat real quickly so everybody can do that, or we'll also be posting these PowerPoint slides. I don't know about, we don't have them yet from our speakers, but if they send them to us, we'll be sure to include those along with the recording soon. So, and with that, everyone have a great afternoon and an awesome weekend. And again, thanks to our panelists, and we'll see you next time. Probably not until the fall.
Thank you. Have a good
Thank
weekend.
you. Bye-bye.
Bye.
Thank
Bye-bye.
you.
Thank you.